See that encoders are very powerful, but they have some problems about how they've been implemented in Spark. And so we will see why their implementation is kind of bad and some way to fix these problems. So for whoever doesn't know what Spark is, Apache Spark is a multi-language engine for executing data engineering and data science jobs. It can scale from a single machine to entire clusters of machines. Once upon a time, when Spark was created, the main abstraction was the RDD, so Resilient Distributed Dataset. And it's quite easy to understand why Spark became popular so far, because with like 7 lines of code, you could run a word count job over many gigabytes of file in a distributed manner, and with quite an easy syntax. So the code that we see here is just reading a file, and the file can be terabytes if you want. It's splitting the line and counting occurrences of each word and saving the result to a new text file. The code is quite simple, but it can run in parallel in distributed nodes, and it retries failures automatically. So if for some reason some node goes out of memory, the task gets rescheduled and the executor is restarted. And in the end, you will get your result. It's quite obvious why everyone who used MapReduce loved Spark and RDDs, because the same job that I just showed you in Spark is this much code in MapReduce. And actually, this is just for a very simple use case. So, okay, Spark got an easy one over MapReduce, but there was something else that was very popular and much more loved than MapReduce at this time, and that was Hive. So I won't go in detail about Hive, and Hive is still very popular and very, let's say, important piece of the big data ecosystem, but very briefly, Spark offers a SQL interface for writing MapReduce jobs. So the MapReduce job that we have written in Spark and MapReduce, sorry, the word count job that we have written in Spark and MapReduce can also be written with this SQL query, which makes it much more accessible to everyone that uses and knows SQL. So what they did, well, they took the occasion and said, okay, we have Spark, we can also create Spark SQL. So Spark SQL is a module of Spark that works only on structured data. And unlike the RDD API, when you run Spark SQL jobs, you give more information to Spark than the one that you give while using directly RDDs. And a data set in Spark SQL glossary terminology is just a distributed collection of data. And that was added in the last measure release of Spark 1. And this new interface adds the benefit of RDDs. So you have strong typing, and you can use the Lambda function that we love, but you also have the benefits of Spark SQL execution engine, which is more optimized than the default, let's say, RDD one. So this extra information that we got from Spark SQL is used by the engine to perform optimizations under the hood and make our code run faster in the end. So either you use directly SQL or the dataset API. In the end, the same engine will be used by Spark to run your computation. And Spark SQL is available both as a programmatic SQL API like that. So you run methods that resemble SQL statements like you do in Hibernate frameworks or things like that. Or you can just run ANSI SQL, and that is much more similar than to Hive and HiveQL. But yeah, the good point about Spark is that there is not only the SQL-like API, but you have the dataset API where you can perform typed operation like the ones you do on RDD. So the same word count can be done using flat map, group by, and count like we did on RTDs, but taking advantage from the SQL engine and the extra optimization is able to do. So this unification in the dataset API means that you can switch from the functional API to the expression API, so the SQL API, when you need to. So you can write what's most natural in the functional API with that API and use SQL when it's easier to write SQL. So data frame is just a data set organized into named columns, and it's the equivalent of a table in a RDBMS or a data frame in R, Python, if you know those kind of tools. But yeah, you got those optimization. I kind of said that 20,000 times already. So the cool thing is that the dataset can be constructed from JVM objects and also from a wider array of sources like structured data files like Fargate or ORC, from tables in Hive and external databases. And then you can manipulate it through transformation, functional transformation or SQL. So we say, okay, the original API was the RDD. Now we have the dataset that all the advantages of the RDD, plus they are faster because they have a faster engine. So why RDD is still there? Why they didn't replace RDD directly? And the reason is that the dataset might be very, very hard to work with, especially when the data you are manipulating cannot be represented as a table. And also when the data you are manipulating is not a composition of Spark supported types. So for the first problem, that's known as object relational impedance mismatch. And there is a lot of literature about it. And I'm not exactly an expert about it. So you can Google and get a pretty clear idea of what it's about. But the second one instead resides in how Spark developers decided to implement the mapping between a non-typed data frame and a typed dataset. So in other words, the mapping is how rows, which is the optimized internal representation of data in Spark, can be encoded or decoded to and from JVM objects, which is what we want to use inside our Lambda functions. And this thing inside Spark is called Encoders. So what's an encoder in Spark? This is exactly Spark source code. We will go through a bit of it, so be prepared to read some code. That's the definition of an encoder. And If you are familiar with it, this is a type class encoded in Scala language, and we are just saying that we have an encoder of a generic type T, and for that we needed to know a schema, so which columns compose the data we are going to manipulate, and a class tag. So a class tag is just a way for Scala to know the underlying class that we want to map this row of our dataset into simply. So and if you look at all the Spark signatures that use dataset, you find this encoder type class. In fact, if you do a map in Spark, in Spark dataset, you have this encoder here. If you do a flat map, the same. If you create a dataset from an object, again, you see you have the encoder following you. So every time Spark needs to map a row into a JVM object and back, it requires an encoder of A. And in the end, I think that encoder is the worst type class ever. But why? It actually doesn't expose any really useful capability. So if I try to implement a custom encoder, where do I start from? One possible implementation of an encoder of an int, so an integer number, would be to say, okay, the schema is a struct with a field of name value, and its type is integer type, which is a type supported by Spark. And this class tag is the class tag of int. And if I run this code, so I try to create a data set starting from a list of 3 numbers, that's what I get. So at runtime, I get an exception that says only expression encoders are supported today. And today is, I think, since 2014 or something like that. So it's a very long time that they only support expression encoders. So let's look at what these expression encoders are. Expression encoder is an implementation of encoder, and it has many more parameters and gets a bit more sense than the other interface. So we still have the schema, which was also in the original trait. We have a serializer, and the serializer is a set of expression, and I will tell you what an expression is later. One for each field that can be used to extract the values from an object into an entire row. So if I have a row that has 3 columns, A, B, C, I will have 3 expressions that are a way to extract A, B, and C from the JVM object into the row, and vice versa. So actually, for the serializer, you just go from the JVM object to the row. And this serializer is the other way around. So it's an expression that will construct an object given the row. And in the end, yeah, you still have the class tag. So expression are the Spark SQL way of doing code generation. So transforming SQL expressions or user-defined function into Java code. I won't go in detail with this because it gets quite dirty and complicated and very, very long. But in the end, try to think that when you in Spark write select date time of some field of some column. In the end, that SQL code gets translated to very optimized Java code that is compiled on the fly and then run. So The signature is a bit complicated, but it can be even worse because actually encoders do not compose easily. So if you have an encoder of A and an encoder of B, it's not simple to obtain an encoder of another class which is made of A and B's, and use encoder of A and encoder of B to build the encoder of A and B, or my case class. Another thing that I don't like is that encoders are not derived at compile time, but at runtime. And this leads to a tremendous amount of bugs because the earlier you can catch an error, the easier it's to fix. So if I have a compile time error, I don't even get my code to run before understanding that I made a mistake. While if it's a runtime error, I will get it only when I run it. So if I'm a good developer, I have a unit test that shows the error. But if I'm not a good developer, I realize that on production or development environment. So let's see why it's not derived at compile time and how it can be. So if you ever used Spark and datasets, the first thing you need to do is to import these Spark implicits. And this is where it gets dirty. So implicits are declared here in the Spark source code. So I'll try to make my screen a bit bigger. And if you look here, you have a lot of instances of encoder, and you have one for each basic type. So integer, longs, double, bytes, shorts, and so on. And also for lists, so sequences, maps, and so on. But in the end, where it gets dirty is here. So this one, product sec encoder, or actually it should be, sorry, should be the product encoder. It says, I have an encoder for every type T, which is a product, and for which you can give me a type tag, which is practically this resolves for every case class or tuple. And this is not good, and I'll show you why. Because the Scala compiler will generate the illusion of an encoder for every product. And every case class or tuple is a product, even if you create a case class which has a socket inside and a date. And Spark obviously doesn't not have any clue how to transform a socket into a row. In fact, if we dig into the actual implementation of that thing, you see that this start to use reflection. It points to a scalar reflection object, and if we go to the scalar reflection object, you will see that this is a very, very complex method that works with how types are represented in the Scala compiler, but does that at runtime. So there is this case is a boolean, then do this, and so on. And it's very, very dirty, complex, difficult to change, I would say. But more important than anything else is that it's not extensible. So here you get all the logic, and it's inside Spark. So if you want to extend it, you have to copy all of these, change it, add your types, and now it works. But you have to copy paste the very complex code from the Spark code base, which will break if you update Spark, probably. So it's not a very good idea. So back to the presentation. we saw that everything happens via runtime reflection. Actually, you're not leveraging in Scala implicits because those are resolved at compile time, and it's not caring anything about the compile time. It's not extensible, and it's complex because you need to know very well how reflection works and how Scala reflection works, which is even more complicated than Java reflection. So why did they implement it this way? I don't even want to know. Probably the guy who was given the task didn't know Scala that well, was a very good Java programmer probably, but didn't know the strengths of Scala. So I want to ask a different question, which is, are we able to fix it? And the answer is yes, we can. So what we want to fix, there are two levels of fixing this. One is the unsafety. So we don't want to have encoders that at compile time look good, so they compile, but actually are ticking bombs. So as soon as you run that code, it fails. And the other thing we want to fix is the composability. So we want to be able to have a way to create custom encoders and yet reuse them in a safe way. So for this talk, we are going to focus on the first part, and the composability will come later in our next talk. So the first rule is to avoid to use Spark implicits because they ruin the party. And the second rule is the same. So actually what we want is that we want to have our set of implicit instances isolated from the Spark ones, which expose the same implementation, because we don't want to deal with all the hard stuff that we just saw in the Scala reflection class. But we want to have them only when we statically, so at compile time, know that an encoder is actually possible to derive. So how can we do that? Let's define another type class that it's called safe encoder. This is the Scala codification of a type class. So you create your class, which is generic, and you create a summoner method that says if you have an implicit safe encoder for A, okay, I'll give it to you back. It's some tautological, but it's the standard way of doing this in Scala, unfortunately, in Scala 2 at least. So now we need a way to generate usual Spark encoders only when we can prove we have one safe encoder. And this is quite simple. We create a static method, safe encoder, for a generic type A, and we ask for the proof to the compiler that there is a safe encoder of A. And if we do like this, we get a compile time error, which is no type tag available for A because expression encoders wants a type tag. So we just add also the implicit type tag here, and we are done. So we got there. Now we have we need to have an implicit way of summoning it, and we just create another static object and put an implicit definition that simply calls the method we have implemented earlier. So let's try to use this. If we write this code, we get this compile time error, which is not very fun because we were able to encode the ints with Spark, and now we have put something on top and we are not able to encode the ints anymore. And we get this unable to find encoder for type int. So it's easy. Let's define a safe encoder for type int, and the implementation is very straightforward because we don't want to actually give any kind of implementation to our safe encoder. Our safe encoder is just there to prove that that type has a Spark encoder. So it's not doing anything. It doesn't have any implementation. It's just a proof that it exists. And we do that for int because we know they are supported, and we should do that for every supported type. And so we just mix these lang safe encoders, lang because I would put there all the basic languages types, and we mix with our safe encoder companion object of the safe encoder type class. And now, if I run the same code, it actually compiles, and we get a data set of int. So far so good, but yeah, we should add implementation for double, strings, whatever we think. And yeah, this is nothing interesting because Spark can do the same, and you don't even need to write any kind of code. So we saw earlier that something like the following is not a compile time error in Spark. So if you have your Nightmare class with a server socket and a local date, this simply compiles in Spark, but gets to a very nice runtime exception at runtime. So our goal is to make it a compile error when using safe encoders, while making it not a compile error to have something like a case class with a name of type string, which is a supported type, and an height of type double, which is another supported type. So only case classes that are made of legal components can be part of datasets, and we want to be sure at compile time about that. So in order to do that, we need to dig a bit into how these things are implemented in Scala and what is generic programming. So generic programming is a meta programming, and actually the idea is that the types are helpful because they are specific. So they show us different pieces of code fit together, and help us prevent bugs and guide towards solution when we code. But sometimes types are too specific. So there are situations where we want to exploit similarities between types to avoid code repetitions. So for example, if you have an employee with a name of type string, a number of type int, and a manager of type boolean, and an ice cream, which is a completely unrelated type, but it still has a name of type string, a number of cherries of type integer, and an int cone of type boolean, you can see they are similar, even if from the type point of view, they are completely different and are related. And so if we want to write a method that, for example, serializes those two classes into a CSV file, the method would be very similar. But we have to write two different methods, even if they are very, very, very similar. So generic programming is about overcoming differences like this. And Shapeless, which is a Scala library, makes it very convenient to convert specific types into generic types that then we can manipulate with common code. And for example, we can use this Shapeless code to actually transform an employee to a generic employee, which in the end is just a concatenation of a string, of an int, and a boolean. And we can do the same with the ice cream. And you can see these two types, the type of generic employee and the type of generic ice cream, are actually the same because are a concatenation of string, int, boolean, and an empty list. This is exactly the same as this. So we have generalized the type so that we can write common code to convert both of these. Now they are the same type, which are heterogeneous lists, and they contain string, int, boolean. For now, the point is that we can serialize each value with the same function. So if you have a generic representation, which is an heterogeneous list, we can write this code and we can create the CSV for the employee and for the ice cream with the same method. So we need to know a bit about algebraic data types to understand this and their generic representation. So ADT is something I'm kind of obsessed with. The name looks scary, but actually are a very, very simple concept. So ADTs are data types that are divided into two categories, and they are just an idiomatic way of representing the data using and or ors. For example, a shape is a rectangle or a circle, and a rectangle has a width and a height, and a circle just has the radius. So in ADT, you have and types that are called product types and or types, which are called co-products. And in Scala, they are represented like this. So co-product is a sealed trait with some implementations. For example, shape can be a rectangle or a circle. And a rectangle, in its turn, is a product type because it has both a width and a height. And also circle is a product even if it has only one field, which is the radius. And the good thing about ADTs is that they are type safe, and the compiler completely knows all possible instances of ADTs at compile time. And so we can write methods like this, where we are able to calculate the area of a shape simply because we know there are only two shapes in our world, which are rectangle and circle. And so we match on the type and we just calculate the area. And we can invoke it with a rectangle or a circle. So tuples are a generic representation of products. Unfortunately, the scalability in tuples have some disadvantages that make them unsuitable for shapeless purpose, so for generic metaprogramming. And in Scala, each side of a tuple has a different and a related type that makes it very difficult to write code that abstracts over. So if you have a tuple of one element and a tuple of two elements, they do not share nothing from the type system point of view. And also there is no type for zero-line tuples, which are kind of useful. For these reasons, shapeless uses a different generic encoding for product types, which is the heterogeneous list that we have shown earlier. And an H list is a recursive data type, which is either an empty list or a pair of a head and a tail, where H is just the head of the list, so it's a type, and T is another H list, so it can be an empty list or a list with some types in it. And because every double semicolon has its own H and T, the type of each element is encoded separately in the type of the overall list. So you can do something like this. This is a type that says I have a string, I have an int, I have a boolean, and then I have nothing else because there's an empty list. And we can retrieve the head and the tail of types, and types are preserved. So if I try to do head, I get a string. If I do tail then head, I get the second element, so an int, and so on. And also the compiler knows at compile time how long the list is. And so if we call tail too many times and then head, it just doesn't compile. So another thing that shapeless offers is a type class, again, called generic, that allows us to switch back and forth a concrete type and its generic representation. And there is some magic behind it. There are some macro, but in the end, we can get the generic of an ice cream, which is a case class. And the instance of generic as a type member containing the type of its generic representation. So ice cream generic is an H list, as we saw earlier. And the type class offers two methods: one to convert from the representation to the actual type, and the other way around. And if two ADTs are the same representation, we can convert back and forth them using their generics. So I can create an employee and get the generic representation of an employee. Sorry, I can create an ice cream and get the generic representation of the ice cream and build an employee from that generic representation, which leads us to a strange employee of name Sandy, but works from the type system point of view. So we've just seen products in detail, and I will skip the co-products because they're not relevant for Spark, but the title of this chapter is a link to a very good guide about shapeless. So if you're interested, go look at it. So after this detour, I hope to wrap very soon. Let's get back to Spark. So we said we are interested only in products and not in co-products because Spark doesn't support them. And let's try to write a safe encoder derivation for heterogeneous lists. So an heterogeneous list is just a list of types. So the essence of working with normal lists is the recursion, and it's actually the same for heterogeneous lists. So let's define the base case of our recursion. The empty list, or in case of each list, is H nil. And we say we are able to build an encoder for a 0-column table. I would say yes, it's very easy. We don't have to encode anything. And let's try to do it instead for an H list. So a list which has at least one type, one element. And we say we can build a safe encoder for V concatenated with T, where V is whatever we want, a generic type, and T is a subtype of a list. And we say we are able to do that when we are able to find an encoder, a safe encoder for the head and a safe encoder for the tail. And that's mainly it. It sounds weird, but actually it's very simple if you think about it. It's just if you have the head and the tail, you can put back together and you have the list, the entire list. And you can do it recursively. So if you have a 4 elements list, you start with the empty list that we defined earlier, and then put the empty list as the tail and the encoder of the first element. So for example, a string. And then you have the encoder of a string and the empty list. And then you have an int. And then if you have the safe encoder of an int, you can put it in the head, and you have the safe encoder of int, string, and empty list. And you can go on and on and on until you are able to have the safe encoder of the head of the list. You are able to build the safe encoder. So we saw that through generic, we can go from the specific representation of our ADT, so our case class, to the generic representation of it. And we can also do it the other way around. So we implemented everything for each lists. Now we can do it for all products. And this is a bit more complicated, but it's like cargo cult programming. This is always the same. You just say, if you have an encoder for G, which is the H list in our case, and you have a generic representation that goes from F to G or from G to F, well, you actually have the generic representation, the safe encoder for F. It's quite tricky to look at, but if you try it on your own, it makes sense, I promise. So let's try to validate this thing. Well, we have our app, and if we do the old example, it still works. But now, if we try with a case class, which has a string and a double, it works too. We can actually encode our dream class into a data frame. And it works with tuples too, so we don't have the case class, but we have a tuple of 2 elements. It's the same. It was thanks to Shapeless. But now, and here's the good thing about what we did. So our goal was that Nightmare wasn't serializable, and we wanted to know it as early as possible, so at compile time. And if we try to do what we tried to do earlier in the presentation, so build a data set of nightmares, actually we get a compile time error which says unable to find encoder for this type. And if we try to follow the advice of Spark developers that says import Spark implicit, well, we are violating the first rule of the Fight Club. So we import it, and we change the error from a compile time 1 to a runtime 1. So we get it only if we have a unit test or something like that. But if we go straight to the running environment, we will lose a lot of time. And also running test is like losing time because they take time to run, especially if you have Spark running inside your JVM. So to recap, the type classes are cool, but encoder, which is a type class, is not cool. But we can fix it, partially so far. We can do better. We will see later. And it's not much code. It's just some 20 lines of Scala code and a lot of boilerplate for the primitive types. So I hope I didn't annoy you too much with this presentation, and I hope to see you, all of you, for the next part when we tackle the more difficult thing, which is composing encoders, and that unlocks a lot of potential because we can build encoders for custom types which are not case classes, and use those to build case classes of those classes, and on and on. So that was it. Are there any questions? I would say there are not. So anyway, if you have any questions, I will drop my Twitter handle in the chat, so you can send me a message. And if you are interested in the slides, I will publish them soon, and I will tweet the link of the slides so that everyone can have a look at them. Thank you, everyone, and
thank you, Antonio.
Back to you.
Super interesting. Mm-hmm. I also will send to the participant the link with the registration. I will also send you in the chat a link related to this meetup, And this is very useful for us that are organizing these events because we are elaborating feedbacks and try to improve every time the structure and the meetup of the meetup. Also, if you want to propose as a speaker, you can do it with the link. Okay, I will leave the stage this time to Faith. Welcome. And
hello, Dario, and thanks. And yeah, I would start with my presentation on ECS to production, actually. So I will be making a case for, or a use case for actually using Amazon ECS for some of your deployments, if not all, but maybe as you follow, you might get more interested, yeah. So today we would see technically go into container orchestration, we'll speak about the main one, of course, briefly, and then speak about the power and simplicity, and then speak on AWS, Amazon ECS, other services, and maybe a short demo, because I think the time is very short, and then probably take questions after that. Yeah, so next. Okay, so about me, my name is Faith Tosin, if you prefer. I'm a 4-time certified AWS professional. Also, I'm certified. I'm a certified Kubernetes developer and administrator, a community builder, and of course a DevOps, cloud DevOps engineer. So I am very passionate about containerization and cloud native topics. And yeah, so of course a quick recap. I understand everyone here understand what containers are and the use cases, but again, I just want to go back to touch on the evolution of the movement from virtual machines to containerized based deployment. So of course, with virtual machines, we had the host OS, and then of course the guest OS came on with their binary. So each virtual machine will bring its own OS, and then we move to sort of evolution. We evolved to containerized based deployment, where the container engine runs on top of the operating system of the host, and in this case, maybe you have a Docker daemon or Podman, any sort of container engine you're using, and then applications and binaries run on top of that. So something more, what's it called, the standard way to package your application, OCI compliant images and whatnot. And of course, with this came other issues, definitely. We had the problem of orchestration. So technically with these containers, we had to provide security to them, provide elasticity. So technically we get more traffic, we want to scale up, the traffic goes down, we want to scale back down. We want to integrate with, of course, other services for load balancing, for logging. We actually have to now manage networking among those containers. So things like service discovery, service meshing. Also, storage became sort of separated. With VMs, you can attach storage, you can attach compute, but with containers now, you have to technically deal with storage and things like secret and configs and whatnot. So of course, straight up to Kubernetes. Everyone knows Kubernetes, the container orchestration tool of choice now. Very popular, doing great. Of course, Kubernetes provides you with a sort of cloud agnostic object, where you can technically write your Kubernetes object in YAML, of course, declare them in YAML files and have them deployed to even AWS, to GCP, to Azure, or even you can even self-host this object. And of course, it's an open source tool, and it's we get it. What's it called? It's the top container orchestration tool right now. But with its beauty also comes complexity. Yeah. And this is a quote from Drew Bradstock, which is the product lead for Google Kubernetes engine. And he technically says that despite 6 years of progress, Kubernetes is still incredibly complex. So I understand that once you deep into the complexity, for example, personally, I really enjoy using Kubernetes and deploying applications through Kubernetes. But for organizations, deployment time can be high, and even for engineers, complexity can rise as applications scale. So there definitely are other ways to technically deploy your container workloads in a production style manner and not deal with the complexity Kubernetes brings. And of course, if you're already in AWS, then using Amazon ECS makes perfect sense because this is a very highly scalable, performs very highly, high performance container orchestration service that supports, of course, Docker containers and allows you to actually easily run and scale your containerized applications on AWS. So with ECS, you can technically scale, run production grade, what's it called, workloads without dealing with complexity that, for example, things like Kubernetes or even EKS, which is another container orchestration tool by Amazon, brings on. And with Amazon ECS Fargate, you can choose to run in two ways. So you can technically run and bring and manage servers, which is in this case EC2 instances or technically virtual machines, or you can run in a mode called Fargate, which is technically my favorite mode, which is technically running serverlessly. Of course, serverless does not mean there are no servers. It means someone else manages that server for you, and you just, for example, specify the compute, specify the memory, the CPU, and specify your image and other configurations, and then your workload is deployed, and then you can manage that instead of managing, for example, the server behind it. And we would, of course, take a deeper look into Fargate today, but before we move into specifics of Fargate, we should technically understand how ECS works. So for Kubernetes, we have Kubernetes objects, you have deployment, you have replicas, you have what's it called, pods, and you have things like services, you have ingress. So the same thing with ECS, you have something called a task definition, which in this case I would relate to pods. If you already understand Kubernetes, you understand that pods is the smallest unit of the object you can technically communicate with. So with pods, you can set your containers, give environmental variables to those containers, and set compute, request, and limit. So very similar. Task definition is also a JSON file used by ECS. So in the task definition file or in the JSON file, you technically specify how your container should be run. So you specify things like the image name, port mappings, you specify even container and host port, you specify memory, CPU, and other things, yeah, even volumes, up to volumes, yeah, and even networking mode. So this is an example of a declaration for JSON, for task definition JSON. Of course, mostly you would not write in the JSON file. You will be using the sort of task definition builder on the console, or even maybe using infrastructure as code tool like Terraform, like CloudFormation, to make this deployment, which makes it easier because, for example, CloudFormation gives you a YAML template to declare your containers or your task definition in, and then Terraform, you can use the HashiCorp language to technically declaratively create your task definition. And outside the task definition, we have something called service. So with service, I would technically call service the combination of a Kubernetes service and the Kubernetes replica, yeah, and also deployment, yeah, because technically in this case, service ECS service actually manages the number of tasks, desired tasks you want to run. So you set the number of tasks you want to run. You set the scaling rules you want to, in case you want to scale based on specific rules, which we will see very shortly. You also specify the load balancer configuration. You do service discovery on there, and then you set deployment types for continuous deployments, like in case you want to practice rolling update or blue-green deployment. And if you look at the image on your screen, you can see that with a service, you actually have tasks running within services. And you can have, of course, multiple tasks running in a service, but again, a one-to-one relationship is advised, so you can technically manage these things even easier, so you don't raise the complexity again. And again, with services, you also have clusters. So cluster in this case, I would relate it to schemically to a namespace where it's a logical separation or logical grouping of your tasks and services. So technically a wrapper. And of course, you can also run tasks directly on a cluster without using services. But if you want to have a layer of control over the networking, over other components, then you should technically follow this best practice of running the cluster, or running the service in a cluster, and then running the tasks in the service, and then you can have your containers in the task. And with ECS, what do you get really? What makes it easier? So with ECS, you have technically integrations with a lot of AWS services out of the box. So for example, with Secret, you can ECS integrate easily with Secret Manager and Parameter Store. So you can specify ARNs or resource numbers of secrets and what's it called, and parameters map them to environmental variables and use them directly in your containers as environmental variables. Elasticity, of course, is another point where ECS is closely knit or tightly knit with auto-scaling rules, auto-scaling service actually. So you can set up an auto-scaling rule in very short period, and then you're able to scale based on CPU utilization, memory utilization, or even number of requests from the load balancer, for example. And also another component is load balancing. With load balancing, you can attach elastic load balancer, which is an ALB or an NLB to ECS, and then you can technically configure this separately away from ECS and have that dealt with, and that another layer of abstraction or another layer of complexity moved out of ECS itself. And with networking, you can manage your VPC also. You can have a VPC that you technically create for your workloads, and you technically deploy your ECS workload into that VPC. So networking is also managed, or it's not managed, but you can you have another layer of abstraction technically managing networking with VPC. So you can deploy your containers in a highly available manner into different subnets. You can configure if you want external IPs and really do complex networking stuff. So service discovery, you leverage Cloud Map and Route 53's high availability, and you can practice service discovery in I think 3-4 clicks. And service meshing also with App Mesh, you integrate closely, and of course with image registry, which is ECR is like a image registry for Docker images. So this maybe you don't use Docker, or maybe you don't use Docker Hub, or you can actually even still use Docker Hub, but ECR is there for you and closely very integrated with ECS. And storage, you have EFS, which is a network file system for an AWS service technically, also very closely knit with ECS. And of course, you can also use bind mount, which do not require any external services. Logging and monitoring, you can do that with CloudWatch, closely integrated also. And then you can also use tools like IAM to control the access your ECS containers actually have to other AWS services. And you can also use code deploy to technically, automate your deployment to ECS, which is actually another cool part. So I will get into a demo. Actually, the supposed demo should be, for example, a service or a front end exposed with a load balancer. And of course, we have the DNS managed by Route 53. So this technically shows you how integration with different services helps ECS. So definitely we have a DNS provider with Route 53. We have the load balancer, of course, and in between this, you can use ACM, which is a certificate manager to manage, to technically encrypt, traffic in flights and do SSL. Seamlessly also specifying ARNs, and then load balancer can technically can transfer load to workloads in different availability zones. So for example, one easy goes down, you have other easies up. So in a high available manner. So let's jump to the console. And actually before this, I deployed a sort of I would say demo environment. So I deployed a container with a load balancer in front of it, and of course attached a DNS name to that with SSL certificate, just to show you how easy this is. So we will go through a very similar process in this demo. So this is the ECS console. There's a new one, but most features are not yet on the new one. So we can technically go to the first page. So you see we have a cluster, which is technically a namespace or a logical separation of different ECS services. So we can create a cluster. And in this case, we are speaking about ECS Fargate, so we don't have to deal with EC2 component. So EC2 is technically dealing with virtual machines or underlying virtual machines. So let's just go with Fargate, and let's name this ECS cluster 2. And we don't need to create a VPC from here because I already have a default VPC that I'm running on. So creating that cluster, you see there's a sort of a box created where you can technically walk in and deploy different things in. So we would technically create a service, or let's actually create a task definition first, so you see how that works. So let's create a new task definition. Of course, we are using launch mode Fargate, and I think we have the next step. By the way, if you can't see my screen, just notify me. I can probably even increase the size. Okay, perfect. So we have the tax definition name. You can name this anything. So let me call this ECS 2. And then the tax role, this technically helps you to manage accesses to AWS services. So you can, in a secured way, using policies, limit the access the container has to other AWS services. So for this, we don't need any, but I'll just attach one of the default ones I already have. And then, of course, with ECS, you can also deploy not just Linux workloads, but even Windows containers. I don't know why anyone would want to do that, but yeah, I prefer to run Linux workloads every time, of course. Of course, there are different use cases. Maybe your company is working with Windows services, and you want to actually containerize that. Why not use ECS? So with tax execution role, actually, this is the row of permissions you need to pull secrets, to pull images from ECR. Technically, a role to help you start your container. And with this, if you're using ECR, you technically want to make sure that this role has the permissions or the policy with the right API permissions attached to this role. Yeah. So like I said, with Fargate, you technically just choose your memory and choose your CPU, and then you're good to go. You don't deal with the underlying virtual machine. Yeah. So for this, I will choose the 0.5 gigabyte of memory, and then go with the lowest CPU also. Because I don't want to spend a lot of money here. Again, it's not so expensive with Fargate, because again, you pay for only what you use. So even if you provision this and there is no traffic coming to this, you pay very, very little amount here. So with the container name, let me call this ECS container. Let me add the two flag in case I've technically used that. And this image by default pulls from Docker Hub, so we can specify technically an Nginx image. Yeah, default Nginx image. You can add a tag latest or not, but of course, by default, we'll put the latest one. And you can use private repository authentication to ECR if you wish, or if you have that set up. Of course, security is cautious, is a thing of cautiousness here. And you can add, of course, if you're used to Kubernetes, you can add memory limits in this place, and add software add limits to technically limit how far the containers themselves can go with memory-wise. Yeah. And of course, port mappings. I know Nginx would automatically be exposed on port 80. And with Fargate, you only specify container ports. It has to also match the host port. So you cannot specify, for example, mapping of container port 80 to host port of 8080, for example. Then that would not work here. You can specify, of course, these are basic Docker provisions. So a command for your health checks, commands actually, maybe this uses call out of the box. Of course, you can see templates already created for you. You can specify the interval, the timeout, the start period, the retries for your health checks. You can technically set up a CPU unit, GPU. So a lot of options for you to technically set for your containers with the tax definition. And timeouts. Stop timeout, networking configuration. You can disable networking. With Fargate, I think we are only able to use the AWS VPC networking mode. And of course, again, this is storage. You can use, like I said, you can use what's it called, a bound mount, or you can use EFS, which is a network file storage. And automatically, of course, logs are transferred to CloudWatch for us. If you run other workloads, you understand that in other container orchestration systems, you might have to actually start collecting these logs again, another process. So this is out of the box, doing a lot of things for us. Yeah, so I would accept, and we can, of course, again, this is a service meshing. If you need that, yeah, that feature also, enabling proxy configuration for app mesh, which is a service mesh to the service by AWS. Log routing, or maybe you want to use file lengths. Volumes, you can create volumes, and like I said, there's bound mount, there's EFS support. Yeah, so I can create this tax definition, and if I say view task, you can see we use the builder to create this definition, but I can actually export this JSON and copy this JSON. It can be used for deployment, for different use cases, and you can actually version your containers in a version control system like Git also, if you wish. Yeah. So we have created a cluster, we've created a tax definition, now to the service, which is technically the glue. We can deploy this tax definition straight into the cluster, but yeah, it's really interesting to actually use the service to control your tax and set some cool features. Yeah. So launch type, of course, we're using Fargate, and for tax definition, I think, yeah, ECS tax 2. of course, we are using the Linux-based container. And for now, we just have version 1 of our task definition platform. We have a different platform version, and be careful from platform version 1.3 to 1.4 networking change. So if you have, so you can't just switch these things. You have to understand the changes that are being made in them. So the cluster, of course, and then let me set the service name ECS service, the to flag. And number of tasks. So this is technically the replica part, or the what you would call the Kubernetes replica object part baked into Fargate or into ECS. So for example, I want one number of tasks to run at all times. Of course, this can vary depending on the scaling up and down rules that I set. And of course, also with deployment, I can set rolling update or blue-green deployment, of course, to make sure, for example, containers are LD before traffic are sent to them. And we can, of course, go to the next step. And this is where networking, I think, comes in. Okay, so we choose a VPC, which is technically virtual private cloud or sort of network for our workloads. So choose subnet, and when containers come up, they are deployed into one of these subnets randomly. So if you want to be highly available, then you select as many subnets as possible, of course. And in case one subnet loses connection or goes down, the container is deploying another one, and you're really highly available. And then you can also be very secure with security groups and technically filter out maybe the sources of traffic, or you want traffic to come from specific IP address or specific security groups. Actually, you can actually also do that. And with IP addresses, you can say you don't want this container to have a public IP, but in this case, I would leave it as a public IP. And with ECS Fargate, actually, it's cool that each container we have an ENI attached, which is a network interface. So that network interface will have its own public and IP address, public and private IP address. So it technically is you can protect that, of course, with security groups and keep that on lock as you wish. And you see again within the console, we have a possibility to integrate with the application load balancer, the network load balancer, or the classic load balancer, which has actually been deprecated. So, for example, let's try to attach this to an application load balancer. And the load balancer name, I have a default one called ECS demo. Okay, we have to set the routing rules, but let's attach that for now. Or interestingly, I might actually want to create a new one. But let's do this for now. And container name and port. Okay, yeah, good. So let's add to load balancer, and then HTTP 80, and then default path, evaluation order. Let me put this to 2 in case there's another rule there already. And yeah, correct. Check path, okay, on the default path, because of course we are deploying an Nginx image, and on the default path is to give you the welcome to Nginx image. And of course, we're using HTTP protocol for our target group. And we have no app mesh configuration. And service auto scaling. So imagine we want to scale as traffic increases. So the minimum at all time, maybe you want to have one minimum number of tasks or number of tasks. That's the installation of our containers. And maximum, maybe you want to scale to 5 in case traffic gets really crazy. And of course, you need your service needs a role to be able to create new containers on your behalf. So everything you have to give permissions to these services to do for you. And scaling policy, in this case, I train target auto scaling. So technically, you want this technique how I would say the AC works. So technically, I want you to get me to 50 degrees. So if, for example, in this case, if I set up 70 and I put CPU utilization, so immediately it crosses that 70, then scaling starts, scaling up starts, and immediately the average CPU utilization drops below 70 again, scaling down starts. So let's call this ECS policy 2, just something. And then, of course, there's a cooldown period. You just don't want to scale down immediately. Target value drops below 70%. It can be a false alarm. We just want to give time for traffic to actually normalize, and you can actually play with these and check what works for you. So next step, I think we've covered a lot. And let's hope it creates successfully. This is coming up. And then let's view this service. So, of course, I think I expect the containers to fail initially because probably I have to go to the load balancer to change some routing policies. Okay, so you can see technically the task is coming up. It's provisioning, and while it provisions, let's move around the service tab. So you can actually see every event that occurs. So this is very similar to doing a kubectl describe pod, for example. You can see the events that happen, and you can actually even troubleshoot with these events. So auto scaling again, we set maximum number to 5, and we set target auto scaling, and so with just this, we have auto scaling already set. And you can even also do for example, memory utilization, or combine those metrics and scale based on the combination of those metrics. For deployment, this is technically closely integrated with code deploy, which is a continuous delivery, continuous deployment tool by AWS. So if you have a CI/CD pipeline, it very, very much closely knitted with ECS, and really helps you speed up your automation of deployments. Yeah, so you can see metrics for your container and for your service generally, with CPU utilization you're currently using and the memory utilization here. So of course we have nothing here because nothing is coming up yet, and I think it takes 5 minutes to see the latest metrics, and you can see logs here technically, and we can see instantly we're already getting what's it called, HTTP GET request on the default paths for our container, and that's been set by the load balancer, I suppose. And yeah, if we go to the load balancer, you can actually go see if this is, or before we actually go to the load balancer, let me see the tax. It should be up. And like I said, this has its own IP address. You can see the public IP. So if I hit this public IP, we should actually see Nginx welcome page. Yeah, definitely. But of course, in a production environment, you're not technically you're not managing these IPs yourself. You want a component, which is a load balancer in this case, to manage these components for you. So we can technically go to, before we go to the load balancer, let's check the target groups. Actually, target groups is where the health checks are done. It's where you can see what's happening. Let me see health checks. Okay, let me just click this so we can track it. Yeah, okay, it's actually very healthy. So you can see as containers go off on go up and down, or go off and on, this is where they get added to, like a sort of I can't call this a registry. It sort of acts like a registry. Definitely, it keeps the IP address, and it technically a lot. The load balancer sends traffic to these based on the number of containers available, of course. And you can set the health check rule. In this case, we are doing normal HTTP protocol and sending a call. Technically doing a call or a GET request to the default path, and doing, of course, the health check rules that we've set initially. 300 seconds interval. We are expecting a success code of 200. And a quick hack for you might be, if you deploy your workload, maybe you're deploying maybe a Django workload, and in most cases you can get a redirect. So most times you see 200 is HTTP status OK for status code for OK, and it's what most people would expect. But sometimes your application is just redirecting and is not even broken. So you can technically add more status codes that you actually know to be LD for your container, and then you can mark that so the load balancer knows that can actually also be LD. So this is for the target group, and you can actually set cool attributes. Okay, I think this is not to talk about target groups or load balancing. So let's go straight to the load balancer to see actually what's happening. So this is the load balancer we're using, and I actually have 2 rules set. Yeah, 2 listeners, one listener on port 80, another listener on port 443, which is the default port for HTTPS. So that's where this is coming from. For example, the Agile Lab Cloud Academy demo with SSL, everything secured, is using that port 443 and attached to ACM, which is a certificate manager. So I'm just trying to show you how closely integrated these services are, and how your life can become extremely easier. Especially for maybe you need to even demo something. You don't have to move your whole workload to ECS if you don't want to, but to technically demo a service, demo a product to a customer, or maybe even run some data workloads. I know you guys run a lot of data workloads, and yeah, it'll be very useful. So with this, we have rules. Let's see the rules we have currently set. So this is our rule. So the default part is it's on the default part, and then it's of course on port 80. Forward this to this what's it called, this target group, which is what's it called, our default, which is our container we actually just created now. So that's what I'm actually using, that load balancer for multiple services. So I can actually use that to show you different different rules. So on the default path, I would get Nginx. Of course, this is Nginx. But on if I change this path now to tutorial to /tutorial, then it would direct me to demo. So let's get the what's it called, the DNS name of the load balancer, because the load balancer will give us a DNS name, and then of course I've attached that to Route 53 if I want. Actually, I think yeah, it's attached to Route 53 already, and I can try to. Okay, let me go back and actually first use the DNS name to show. Okay, so this is like the load balancer can be mapped to an ingress controller with an ingress, yeah, and in Kubernetes, yeah, very similar. And if I grab the DNS name for the load balancer in this case, and let's see, let me go to the load balancer. Of course, on the default part, on the /tutorial part, it goes to this. On the default part, it should actually be going to Nginx, but I think we have to reconfigure the rules. Okay, so let's actually edit these rules. Okay. Okay, so on the default part, okay, let me remove this. Okay. And then, okay, sorry, I have to cancel this, and then minus, and then remove this row, delete. And then there's only row on port 80. If the default part is / it goes here directly, it should go, yeah. Okay. Okay, so we'll just, I think, wait a little bit for this to change on the DNS level. I think if I technically direct to / now, it's still redirecting me. But I think you should get the point. But we will wait, and I will try in a couple of seconds. Yeah. So let's, for example, okay, let me actually detach the other listener and make sure this is actually going to only one service. Sorry, let me edit this. Okay, so I want this to actually go to ECS service 2. Okay. View the listeners again to make sure. Okay. Edit the HTTP2 to make sure. Okay, I want this to do that. Okay, perfect. So let me hit this endpoint now and let's see. Oh, actually, I can actually use the DNS name now and try to this endpoint. Yeah, so it's technically process our traffic to Nginx. So with that, I technically have SSL set already. Have this send load to my what's it called, to my container. And for example, we can even watch what happens if I try to scale this down. Or let me see. Yeah, if I try to go to ECS and technically switch off, or just let's say there's a crash, for example. Let's see. I go to services. Of course, based on the health check rules that we set, this is constantly checking for oh, sorry, not delete, but I want to go to the tags to put off the current tags. Okay, so let me stop this. And of course, because I've set the desired number of 1, each time I stop this, it tries to actually start a new what's it called? Start a new container. And let's try to actually access. Of course, we expect 500 error instantly. Yeah, because of course the endpoint is the backend is gone, and the health checks shows that the container is gone and is actually trying to drain. So yeah, so you see this. Let me see health checks. Yeah, no packets. Yeah, so it's actually draining because the container no longer exists and it's filling health checks now. And to actually help this drain faster, I will make sure the attribute is set to 30 seconds, so we can have this drain much faster. So traffic is gone away from there. And we go back to ECS console. I'm sure there's a container already coming up to set it, yeah, already running actually, to actually satisfy the desired number of 1 that we have already set. And if I set this to 2, it will also scale up and technically keep trying to adjust to the number of containers I set, or the desired number of tags that I set. And let me see. Let's go to the target groups. We should already see this trying to pass the health checks or trying to undergo health checks. Okay, so health checks, targets. Okay, so we should see a container initializing here. Okay, already actually LD. So this is a container with IP address 172.3.1.7.2. And if we go back to ECS, we can see that this container is actually, private IP 172.3.1.7.2.200. Yeah. So now if I try to access my service now, it's back up. So of course, with ECS, everything is not kumbaya. It's not sunshine. There's some specific, specifically one thing I want you to take note of is that running daemon sets on ECS Fargate is not yet possible because, of course, you don't control the underlying infrastructure. You don't own the VMs. Luckily, at least a feature or a watch out I would have added here 3-4 months ago would have been ability to SSH into your containers, but now there is actually a possibility to SSH into those containers, and of course, it's not. It of course entails you enabling the session, and it actually uses SSM system manager behind. It's possible, yeah. So something you have to watch out for is daemon set, and a workaround for running daemon set is actually just to run a sidecar. Technically run the container beside your technically. Let me take you to ECS. You can see your tax definition. You can actually just run multiple containers in what's it called, in your tax definition. So let me create a new revision. And for example, if I need a container to forward maybe logs, let me see. No, not maybe you're not forwarding logs. Maybe sidecar proxy. Maybe maybe an envoy something. Maybe I'm trying to run envoy. Yeah. So let me call it a sidecar. I can pull. I don't know if this image exists, but of course I'm not going to deploy this. But technically, you can run, instead of running daemon set. Of course, this is more expensive, and you're running technically one sidecar with each desired number of tasks that you want. But it's something to take note of. If daemon sets are really two things you use, then maybe ECS Fargate is not a mode you should be running in. Yeah, so I think that concludes my presentation, and I left actually a useful link for. I know you guys are very data-oriented guys, so deep learning on ECS might be very interesting to you. You can try to technically look at the part of this link. Technically, you can just Google Amazon ECS deep learning containers, then you'll get here definitely if you cannot grab the link very fast. And you can connect with me on LinkedIn. Of course, Olapade is my name, and I think that concludes my presentation on ECS to production. And if you have any questions, I think it is the right time to ask.
Yeah, I think it was very interesting. Also, having a look in the creation of the service. Yeah, I mean, it was really nice and
Thank
easy
you
to follow.
Thank you very much. Thank you.